example from last time. They were all in R2. And we had something that looked like this, right? We had A1 was something, A2 was something, and A3 was 0, 0. What was it again? Really? I think that's too easy. Zero, one, negative one, negative one. That's okay. Let's do the eigenbasis there. Unless somebody can come up with that set of vectors from last time within the next minute. Yeah, Eric, you got it? Oh, V1 was 0, 0? Oh, 2, 1. Okay. Question, is this set of vectors linearly dependent or linearly independent? Try again. Is linearly dependent, what is it? Immediately when I say a set of vectors is linearly dependent, what does that mean? Find a set of scalars that I can multiply to all of them. Not all scalars are 0, and the whole linear combination goes to 0. Could you find a set of scalars that I can multiply x1 times this thing, x2 times this thing, x3 times this thing? One of those are not 0, and the sum goes to 0? What is it? 1 times a1 plus 0 times a2 plus 0 times a3 definitely would be equal to 0, and yet one of those is non-zero. Go ahead, Joe. We would say that, so now you are going back to the other definition that I just erased, right? We would say that the vector 0, 0 is linearly dependent on the vectors a2 and a3 because I can write the vector 0, 0 as a linear combination of the other two. What linear combination is it? The trivial linear combination, right? The one that has a 0 in front of this and a 0 in front of that. No. Did I say that I was trying to make A1 out of A2 and 3? Well, yeah, I mean, yeah. So over here, formally speaking, the definition of a set being linearly dependent, what does it mean? It means one of your vectors can be written as a linear combination. Does it have any conditions on the scalar values that you use in the formal definition of linear dependence here? No, no conditions. But we said it's kind of clunky because it means that you have to identify which specific ones a priori, right? Another way to say this was the theorem that Ryan intuited. He intuitively came up with that theorem was, if we bring that AJ over to the other side, what is another way to think about linear dependence? Linear combination, but in that situation, at least one of the scalars has to be non-zero. So I would go back over here. Which scalar is guaranteed to be non-zero in the way that we wrote this? There's only one of them that actually has a condition on the scalars. Which one is it? That one right there, right?